This talk presents a review entitled 20 Years After Scaling Relations in Oxygen Electrocatalysis and Beyond. The title hints to the fact that the scaling relations appeared in the literature 20 years ago in 2005. As well, it refers to the sequel, The Three Musketeers by Alexander Dumas. The authors are Vladislav, Ritums, Jan, and Nadezhda, and that review is available at Gamma. I'm Vladislav, and I'm a big fan of classical literature, and thus I would like to begin with a quote of Leo Tolstoy from The War and Peace. It's given here, and it is about a boy dreaming to eat an apple from an apple tree, and the apple is falling. I actually like this citation because I recall it whenever I try to simplify my research and try to explain something with simple terms like scaling relations. So I have rewritten the quote for oxygen reduction reaction. And it says the following. When an oxygen molecule absorbs and it is reduced, why does it turn into water? Because of the potential drives electrons to the surface? Or because the absorption energy is just right? Or because the surface geometry suits the interface? Or because the proton supply is fast enough? Or it's because the girl measuring the RDE once saw. Nothing is the cause. All this only the coincidence of conditions in which all catalytic events take place, including limitation by the scaling relations. It is fascinating that across different scientific fields, the progress often reveals a hidden constraint which takes time and creativity to overcome. Thus, this slide shows 4 cases: a combustion engine, a wind turbine, a solar panel, and a fuel cell. Each represents a point in history where performance began to plateau. The pattern is very familiar. A promising technology emerges, then a physical or chemical principle sets a hard limit on unit level efficiency. To move towards, we don't break the rules. We actually change the system. We rethink what the unit is and how it works. For engines, combined cycle design rises to efficiency beyond what simple thermal cycle can do. Here you can see that gas turbine combined engine is pretty efficient. And in photovoltaics, tandem cell surpasses the Shockley-Quasar limit for single absorbance through double-triple junction. Wind energy advances not just by improving the blades, but changing the tower height and the park level layout. So in electrocatalysis now, we're standing at a turning point. Scaling relations set a ceiling for the performance on single atom sites, but as we see further, by introducing multi-atom sites, we can circumvent that limit. So this presentation builds on that idea. We classify the strategies that manipulate scaling relations in analogy to the breakthrough in other technologies. The central topic is simple. Unit level limits exist, indeed, but the system level solutions remain open.
I'm Ritums, and I will guide you through the basic concepts we will need for the rest of the talk. These include overpotential, scaling relations, reaction mechanism, and activity volcano. Let us begin by examining what defines the efficiency of electrochemical energy conversion, using the example of water splitting and its reverse in fuel cell. In the left-hand side panel, we show standard polarization curves, current as a function of potential for the fuel cell reactions. Rather than discussing hydrogen, let us focus attention on oxygen side, where the main energy losses occur. Here we have oxygen evolution and oxygen reduction reactions. Specific points on these curves mark the selected power potentials: 10 mA per square centimeter for oxygen evolution reaction and 3 mA per square centimeter for oxygen reduction reaction. These current densities serve as benchmarks and allow direct comparison of catalyst performance, all reference to platinum-111 surface. Using these values, we also introduce our potential, the difference between the thermodynamic equilibrium potential, which is 1.23 for oxygen reduction reaction, and the actual potential needed to maintain the benchmark current. The overpotential quantifies the extra driving force required to overcome the thermodynamic, kinetic, and steric limitations inherent to the catalyst and the interface. Considering the efficiency, the arrows indicate two key values: the applied electrolyzer voltage and the fuel cell voltage under load. Taking the ratio of these voltages yields the round-trip efficiency. In the right-hand panel, take a look at the timeline of the highest recorded power potentials for oxygen reduction and oxygen evolution reactions over the last decade. We distinguish between platinum group metals, PGMs, and metal nitrogen carbon, MNC, catalysts, to highlight the advances in both classes. Despite this progress, a clear gap remains between the best ORR and OER values, hundreds of millivolts wide. This defines the practical efficiency loss that even our best systems cannot yet avoid. As we shall see, theory connects this limitation to the energetics of reaction intermediates through rescaling relations. Let us now zoom in on the oxygen reduction reaction and extend the perspective over 20 years. You see the highest reported oxygen reduction over potentials. These data points define the frontier of electrocatalyst development, revealing a gradual approach toward the state-of-the-art limit near 0.3 volts. Next, we shift to computational predictions that arrive at the same value. The shown points are calculated from absorption energies of reaction intermediates and mapped on the so-called volcano, which reflects the Sabatier principle. The optimal performance emerges from binding the oxygen OH intermediate neither too strong nor too weak. The three-dimensional volcano is a theoretical framework. It captures a multidimensional energy landscape and serves as a predictive tool for catalyst design. Beneath all this lies conceptual chemistry, the reaction mechanism. As an example, you see both associative and dissociative pathways of oxygen reduction reaction on a metal nitrogen carbon catalyst. On the right, we collect empirical observations. On the left, we present theoretical models. Above, we show what can be measured in laboratory. Below, what can be simulated by computation. All of these perspectives are connected by a shared constraint, the scaling relations. Let us take a broader perspective on how the volcano concept emerged and became widely used in electrocatalysis. You see a timeline that tracks the growing number of publications in the past 20 years. It reflects the rising interest in the oxygen reduction reaction, but also shows how ideas like Sabatier principle and scaling relations gain traction. The notion of volcano plot, once a niche idea, has become a central organizing tool for catalyst design. Next, we visualize the ideal catalyst. An ideal oxygen reduction reaction catalyst would deliver a limiting potential of 1.23 volts, meaning it drives the full reaction at equilibrium with no overpotential. This is a theoretical extreme, not yet realized in practice. Instead, most real and virtual materials fall along the constraint path, the magenta line, dictated by OOH scaling relation. That line separates the best ORR and OER catalysts. To illustrate this concept, I use an artistic rendering of a volcano. The volcano metaphor tells us that one cannot climb a volcano from just any side. There are natural boundaries and accessible paths. Likewise, in catalysts, we are bound to move along certain thermodynamic paths set by the scaling relations. The magenta line is one such path. It defines the only accessible road up. While the ideal catalyst at the apex remains in view, our climb is restricted to this narrow road. That is the conceptual power of the volcano. It shows us where we are, where we could go, and why we cannot get there directly. The mechanism can be complex, even for such a simple 4-electron reaction as oxygen reduction. The pathways of such reaction are numerous and sometimes overlapping. These include proton-coupled electron transfers, side reactions, associative and dissociative steps. This schematic reveals the level of ambiguity we often face when assigning mechanistic details. And yet, despite this complexity, the descriptor of catalytic performance often reduces to a few key quantities. Here, you see a set of linear relationships between adsorption energies of the relevant intermediates OH, O, and OOH. These correlations are known as scaling relations. Scaling relations couple adsorption energies through the chemical nature, valence, and coordination of reaction intermediates. The typical intermediates are O, OH, and OOH. These relations collapse the multidimensional surface chemistry onto a single axis. No matter how intricate the mechanism appears, it is these adsorption energies that to a large extent determine the limiting potential. To begin the discussion, let me clarify the most essential steps of what is happening during oxygen catalysis. The oxygen catalysis of a catalyst can proceed by associative or dissociative mechanism. In both cases, even at high pH, the key intermediates are O, OH, or OOH. In associative mechanism, O2 adsorbs intact and is reduced step by step. This pathway dominates in most known catalysts because it operates at single active site. That is common across surfaces like platinum 111 or MnC materials. The dissociative mechanism, in contrast, involves an early OO bond cleavage. This requires at least two neighboring atoms to accommodate the resulting O and OH fragments. As a result, it has been considered less common but remains an attractive alternative, especially systems where dual atom sites are present. Each intermediate, OOH, OOH, has a characteristic adsorption energy. In principle, you would like to tune each of these independently to optimize each elementary step, but in practice, we cannot. Their energies are correlated by the scaling relations. Scaling relations appear as straight lines when we plot the adsorption energy of one intermediate against other. This means that if you change one, the other changes with it. The correlation is linear and surprisingly robust. It holds across a wide range of catalyst surfaces. Why does this happen? The slope of the scaling line reflects how bonding changes between the intermediates. For example, forming OOH from OH involves adding an OO bond, which introduces roughly one additional bond in the character, giving a slope near 1. For adsorbed O versus OH, where two OH-like fragments form an O2 molecule, the slope is closer to 2. The intercept captures the intrinsic thermodynamic offset, bond dissociation energies, solvation effects, electrostatic stabilization. For example, the OOH-OH scaling has an intercept around 3.2 electron volts. That value represents the difference in forming an OO bond versus an OH bond on the surface. In most studies, we extract these relations from DFT calculations. Using the adsorption energies, we can analyze the predominant coverage and free energy plots to predict our potential. The methodology is described in details in Fundamental Atomic Insight in Electrocatalysis. For now, let us focus on the volcano and scaling relations. Let us now turn to the volcano plot, this theoretical framework that captures the performance landscape of catalysts. The surface of the volcano defines a chemical space, all possible combinations of adsorption energies that catalyst might have. Catalyst sits on the surface. Their position reflects their binding strength. Too weak, and they cannot activate the reaction. Too strong, and they hold onto intermediates too tightly. The optimal performance lies at the optimum where the binding energies are just right. This is the Sabatier principle in visual form. We construct this model by calculating the free energy change for each step in the reaction And using scaling relations, we reduce the number of variables and express the entire system in terms of single descriptor, often delta G OH. But here's the constraint. Catalyst does not roam freely across the volcano surface. The scaling relations impose specific routes. The magenta line represents the conventional path dictated by the scaling relation. For the associative mechanism, the green line suggests a difference relation for the dissociative mechanism. This is why the volcano remains such a powerful metaphor. It shows us not only where the optimum lies, but also the limited paths available to reach it. The shape is continuous, but the movement is restricted. The challenge is clear. Stay on the path and optimize with it, or find an alternative one. To better understand how this framework works, let us break it down through a sequence of views. We begin with the volcano rendered as a three-dimensional surface. All combinations of delta G OOH and delta G OH lie within this space. To evaluate the performance, we define a slicing plane. This is the set of catalysts consistent with the OOH scaling relation. That intersection creates the magenta path. From here, we extract two projections. The first is a side view, the climber perspective. It shows the limiting potential as a function of single variable, in this case delta G OH. This is a classic volcano plot, a peak at the optimum flanked by performance losses from too weak or too strong binding. The second is the top-down view, the helicopter perspective. It shows our potential as a contour in the delta G OH versus delta G OH plane. You see the full landscape of possibilities. The star at the center marks the theoretical optimum. Specific catalysts, however, follow along a narrow diagonal, the scaling path. These two projections tell the same story from different angles. The top view reveals the goal, the side view explains the constraint. Computational fellows and theoreticians remember that every reaction happens dynamically. The reason why we do not explicitly model such a complex process is not because we cannot, but because it is not necessary for identifying the key chemistry. In fact, before the discovery of scaling relations, researchers did simulate very complex interfaces at the very limits of their resources. The real reason we simplified these visualizations down to a volcano is that in nature there are only a few rate-limiting steps, which in chemical terms are very simple. Scaling relations likely describe exactly that crucial chemistry. In practice, here is how a predictive computational workflow looks. We start with the computational space, create models, predict their stability, evaluate absorption energies, and work down to predict relative. For each stage, we use appropriate tools, such as free energy diagrams, microkinetic modeling, and we choose the right computational approach. For calculations, this might be density functional theory or some machine learning model. That does not matter too much these days. It's also worth noting that there are two types of scaling relations. Thermodynamic scaling relations connect absorption energies, while the kinetic scaling relations connect reaction barriers. For further details, I recommend the listed articles, but for the sake of simplicity, let us now focus solely on the thermodynamic scaling relations.
As South is here again, I will introduce a few key terms that we will be using throughout the discussion below. This includes tuning and braking, switching and pushing, circumventing and bypassing, and the concept of coplanar and cofascial dual atom side catalysts. Understanding this will make it easier to follow the strategies and examples in the upcoming slides. When I first started researching the scaling relations, I found it incredibly confusing. There are so many different terms, often used inconsistently, and making it really hard to grasp what they actually meant. Then I came along this article, actually while writing this review, what we talk about when we talk about breaking scaling relations. And this is by Federico Vallejo, who is actually inspired by the book What We Talk About When We Talk About Love. So Federico raises two questions. Do we know of any materials that unmistakably break the scaling relations? And more importantly, if the breaking of a problematic scaling relation is the end of all troubles in electrocatalysis. These questions guided me and my co-authors in creating a classification of all shown terms. Let's sort them in a chronological order and see whether a story emerges. The concept of scaling was first introduced by Jan Rosmeisel in 2005, when it was first referenced as the scaling by Abel Pedersen in 2007. The scaling is a linear relation between adsorption energies of similar adsorbates. In 2011, even Stephenson and colleagues introduced the term tuning, referring to reaching the volcano edge within the OH-OH scaling relation. In 2014, Montemore and Medlin proposed breaking, meaning a deviation from OH-OH scaling relation. In 2015, Vojvodich and Norskov introduced circumventing, meaning any departure from the OH-OH scaling relation. And in 2016, Bush and co-authors used the term switching for an alternative mechanism involving combined adsorption sites, effectively switching between mechanism and scaling relations. Most recently, in 2024, we introduced bypassing, referring to the use of two states to decouple adsorption energies entirely, and all of these terms describe manipulation of the scaling relations. So here we see the strategies on a timeline. In pale, I show a lifespan of each of the strategy, starting from its conceptual definition, for instance, for switching, which means switching to the dissociative mechanism, and it was actually from 2004 or even before. The solid line here indicates when the strategy was actually experimentally verified, for example, for tuning from 2011. And in the top row, you can see the progress in experiments, starting with this nice volcano plots, purely experimental, where the activity is plotted versus the work function. Then introduction of single atom sites where a breakthrough, an experimental volcano plot where the predominance potentials are used in order to quantify the adsorption energies. That's another major step forward. And the dual atom sites with well-defined distances between the adsorption sites. This is definitely the next breakthrough. And so recently, the coherent use of spectroscopy to prove the mechanism is something that is critical for the current progress. Now below you see a progress in the calculations and theories. That starts with definition of the scaling relations in calculations, and then introducing the single atom site models, also plotting the three-dimensional volcano and explaining the scaling relations on that. Also introduction of the models which have dual atom sites, and now hindered by my view, the idea of having adaptive geometry, which can change between two states and thus provides the bypassing strategy. Let us now look more closely at dual atom site catalysts, and specifically on their role in manipulating the scaling relations. These catalysts come in two main geometries, coplanar and cofascial. Coplanar DACs are having two metal atoms in the same plane and quite rigid environments. The catalysis happens on these two atoms and they can synergize their actions. This geometry allows precise control of the interatomic distance, enabling tuning of the adsorption energies through varying the metals. Then it also allows for breaking, like shown here, where you have the stabilization of the OH intermediate. Edge stabilization can happen also on two metal atoms through metal oxygen bonds. Moreover, you can also switch. Two atoms will accommodate the product of the dissociation mechanism. And if there is a specific distance, neither too close nor too far, which facilitates the hydrogen bonding, then we basically can do pushing. Something similar was proposed theoretically for cofacials, and I think it took from 60s of the previous century to prove that no remarkable catalysts were found. Although, in principle, they can also tune and they can also break through that stabilization via hydrogen bonds or through stabilization by metal oxygen binding. And also they can switch by accommodating the dissociation products, and they can even push if the distance is neither too far nor too close.
We have grouped our approach into 5 different strategies: tuning, breaking, switching, pushing, and bypassing. Each one changes how reaction intermediates interact with the catalyst surface, but in its own distinct way. And in the next part, I will walk you through what each strategy means and how it works. One of the most common strategies for boosting catalyst performance is tuning the OH absorption energy. In the associative pathway, we deal with OH, O and OH intermediates, and on a volcano plot, adjusting the OH absorption energy lets us walk along the OOH-OH scaling line without changing its slope. And each catalyst has a characteristic absorption energy that fixes its spot on the volcano. And by fine-tuning, we can nudge it toward the sweet spot, which is usually an OH absorption energy between 0.86 and 0.96 electron volts, which corresponds to theoretical overpotentials. And this approach is well explored, from model single crystal surfaces to single atom metal nitrogen carbon catalysts. The microscopy image here shows a typical metal nitrogen 4 side, while the model on the right illustrates the flexibility in its composition. Microcycles like iron phthalocyanide on nanotubes are especially adaptable, which they can achieve an overpotential of 0.28 volts, which is very close to the theoretical maximum. So tuning doesn't break scaling limits, but it's reliable, effective, and for most studied catalysts still the only practical way to manipulate them. The second strategy is what we call breaking the OOH-OH scaling relation. The aim here is to selectively stabilize the OOH intermediate without affecting OH. If we can do that, say by 0.3 electron volts, we shift the scaling intercept from the usual 3.2 electron volts to about 2.9 electron volts. And on the volcano plot, that means a potential drop in the oxygen reduction reaction over potential to 0.1, 0.3 volts. How do I achieve it? Two common ways: hydrogen bonding from a base, shown here in the cycle, or introducing a second metal atom to interact with OOH. And the pathway is still associative, but OOH gets an extra boost in stability. This isn't just theory. In 2023, Zonk and co-workers used iron phosphorus MnC catalysts, where phosphorus oxygen sites hydrogen bonded to OOH. And in 2024, Sun's group made a dual cobalt molecular catalyst, and spectroscopy confirmed OOH as the active intermediate and measured overpotentials as low as 0.23. So the key point is that breaking can outperform tuning, but only if you're already near the volcano edge. When we have a limitation which is dictated by the reaction mechanisms, one way to bypass it is to switch to a different pathway. For oxygen reduction reaction, that means moving from the associative mechanism to dissociative one. Switching requires two active sites, so intermediates can adsorb separately and oxygen can split into O and OH. And on the volcano plot, you see this is a slope change from 1 to 3. But here's the catch. Two sites alone won't guarantee improved performance. The range where switching actually reduces overpotential is very narrow, centered around an absorption energy of 1.1 electron volt, which corresponds to a minimum overpotential of about 0.1 volts. Also, the side spacing has to be just right, close enough for cooperation, but not so close that they interfere. And examples exist. In 2021, single atom platinum on manganese oxide showed no detectable OOH intermediates in spectroscopy, which is consistent with a dissociative pathway. And in 2024, iron 2 nitrogen 6 dual atom MnC sites were shown to do the same. So switching is possible, but it's a precision move, only effective in a very specific sweet spot. Pushing is a close cousin of breaking, but instead of stabilizing OOH, here we stabilize O relative to OH. And it applies to the dissociative mechanism, which targets the OOH-OH scaling relation. The effect is twofold. We not only shift the intercept, but also change the slope, which brings us closer to the ideal catalyst line. And one way to achieve this is through hydrogen bonding to the OOH intermediate, and another is exploiting geometry, such as the curvature effect in coplanar active sites. And in fact, DFT calculations for curved cobalt-4 models predict overpotential as low as 0.1 volts. In short, pushing is braking for the dissociative route, but unlike braking, it hasn't yet been confirmed experimentally. The last strategy is the most ambitious, completely denying the scaling relation. Here, the idea is to decouple the absorption energies of key intermediates. All it takes is two distinct catalyst states, each with ideal absorption energy for a different step in the reaction. And if we can switch between them during the catalytic cycle, we could in theory achieve ideal behavior with zero overpotential. And on the volcano plot, this isn't about moving along the slope at all. Instead, it's like tunneling straight to the center and jumping right to the very top. And nature has already mastered this trick. In cytochrome C oxidized, conformational changes create the perfect environment for each reaction step. And theory shows we might be able to copy it. Computations predict that the two cobalt-4 dual atom catalysts could adapt two different geometries, each optimized for a different intermediate. Bypassing then is the ultimate goal, a way to break free from the rules entirely, using inspiration from both enzymes and modeling. To bring it all together, we have organized the different strategies for manipulating scaling relations into a single systematic framework. Here on the chart, the star marks landmark virtual catalysts like platinum 111 for tuning, while the circle marks landmark real catalysts such as cytochrome C oxidized for bypassing. Looking side by side, you can see the clear differences in mechanisms. This makes it much easier to decide which strategy to apply or to explain the activity of a new catalyst based on where it fits in the classification. Now, this framework is conceptual In practice, we often work with specific well-known effects. For metals, alloys, and high entropy alloys, these include the strain effect, the ligand effect, and the cocktail effect, all of which operate within the limits of the tuning strategy. With these effects, we're deliberately manipulating the OOH-OH scaling relation, and mastering them is exactly what allows us to design catalysts that are both more active and more selective. Let's look at an example of how structure controls the adsorption energy of intermediates using MNC catalysts. With a single active site, the OOH-OH scaling relation holds, and all we can do is tune it. But if we move to dual atom sites, new options open up. We can now tune, break, and even switch. Add in structural features like curvature, and the toolbox expands further, making pushing and even bypassing possible. So the energy diagram here sums up this idea at a glance, and in the next section, we'll unpack each of these cases in more detail.
Now we are ready for an outlook. We will revise weak versus strong and far versus close. I'm referring to the famous Sabatier principle and to an emerging principle about the geometry. Just summarize all the strategies using correlation equations are shown here. And that means we will be using slopes and we will be using intercepts. And you can see that braking is basically lowering the intercepts here. And also pushing is also lowering the intercept here. And that stabilization can be approximated by about 0.3 eV, which is a standard hydrogen bond. After 5 general strategies, we have examples for 3, tuning, braking, switching, as well as some inspiration by nature for cytochrome C oxidize. And the only missing verification that we could not find in the literature is pushing. By the way, in order to verify switching and pushing, as well as braking indeed, one needs to do the spectroscopic analysis to see and show that intermediates are present or not present at the interface. And the key intermediate here is, of course, OH. Now, these examples, as you can see, they originate from 2000s, and that is famous platinum-3 nickel catalysts. And recently, the catalysts are more complex. They contain well-defined atom sites with at least 2 atoms. There are, of course, examples where you have one specific atom like platinum, but that one also plays in a tandem with iron atoms in the bulk material. Now that brings us back to the Sabatier principle, and that principle states that binding between the catalyst and intermediate must be neither too weak nor too strong to achieve optimal activity. And in all the cases discussed, the absorption energy of OH is the key descriptor, that we are focusing on the OH absorption. And when we predict the over potential, the lower the over potential, so the closer we get to the ideal catalyst, the higher will be the absorption energy of OH. So we start from about 0.9 here for tuning, and then we shift spoof quite far to approximately 1 eV, and then for bypassing the value, the ideal value for the OH absorption will be 123. More precise values are given here. Besides that, the literature suggests that a new principle emerges for dual atom site catalyst, like shown here on the planar case. The distance between active sites must be neither too far nor too long. And if the sites are far apart, they cannot jointly stabilize OH, for example, through that hydrogen bond, or they cannot accommodate OH like this, where we have metal-oxygen bonds, and they cannot accommodate dissociation products like O and OH in case they are very far. If they're at optimum distance, then the reaction can proceed through breaking and switching and pushing and even bypassing. But if it's too close, then the interaction starts to become repelling. So it's also not so good. And that principle should work both for thermodynamic and kinetic scaling, where the same motivation and same explanations for the barriers will apply. Also, it is working for both coplanar and cofascial dual atom side catalysts. Although for cofascials, we do not really have convincing examples of neither break-in or switching, whether for coplanar, we do have example from the literature. And this table, again, it gathers the most important information for that review. It provides the distances for coplanar catalysts, where we are focusing on the distance between intermediates with oxygens, and then we are focusing on the distance between metal absorption sites. And in the brackets, we are giving theoretical, actually, so we don't have experimental support for the coplanar. We do provide those values taking into account experimental data, but in the brackets, these are theoretical estimations for how cofascial catalyst should work. That should be the optimal distance between different atoms, OO and MM. And if everything goes well and we are at the optimum in terms of energy and distance, then the limiting over potential, the minimum, will be as low as 0.3 for tuning and then about 0.1 for breaking switching, and then it goes closer to 0 for pushing and bypassing. Of course, there are open questions. These are questions for which we could not find answers in the literature, at least very convincing answers that we would be ready to put into the review. But of course, these are quite intriguing to discuss. And the very first question is whether high entropy materials can break the OH scaling relation. And here I'm providing a table showing the progress in the research from 2000s. These are mainly platinum-containing catalysts where we have a platinum skin and we apply straining and liganding effects to increase the reactivity relative to platinum 111 surface. And you can see that all these improvements are made within the tuning strategy. Something similar happens on the high entropy alloys. The increase is actually quite remarkable, comparable to platinum 3 cobalt and platinum 3 nickel. And there are not so many studies at the moment showing that we could go beyond the tuning. But I believe that because we have quite interesting environment in the high entropy alloys, and there are the ways to move along the lines on the volcanoplots, I believe there is ample space for research, and there is a possibility to break and switch the scaling relations. Another question that bothered me personally quite a lot, while doing this review, I started to compare different catalysts, and I questioned myself, how do we actually compare them? For instance, we have metallic surfaces, alloys, high entropy alloys, we have metal, nitrogen, carbon catalysts, we have also molecular catalysts. And some examples are shown here. So for platinum, a stable OH and water add layer forms around 0.9 volts, and that we know from experiment and also from computations. But on single atom side catalyst, like shown here, that is MnC material, that is molecular iron phthalate, we don't have such a water add layer. And thus, that means that one of the key changes or differences in how we compare those catalysts is those salvation and other corrections in the equation when we transform the DFT computed energies into the free energies. And those free energies we then use in order to predict overpotential. So these are pretty important transformation going from purely DFT results to comparable predictive modeling. And the salvation term is one of the key because you can see that salvation is definitely different for those. So that was really puzzling, and the literature is quite scarce on that topic. But a recent paper by Favaro comparing activities of various phthalates anions, it actually gives us some hope. And indeed, it convinces at least me that the term of salvations and maybe some other corrections, including the electrical double layer effect, could be accounted. But in general, the way we calculate the absorption energy for OH and other intermediates is all the same for all these different materials. That means that in principle, I do believe that it is possible to run calculations in the same way for different materials, but then apply some empirical corrections with a knowledge coming from experiments so that we put all these catalysts on the same free energy scale, and then we will be able to compare them on the same volcano. Yet, before comparing very different catalysts, we do need to understand at least platinum group metals and alloys. Because you see some experiments on platinum show a slope. So we don't really go according to the theoretical predictions, which is dashed line here, but our experimental results, they form a different slope of 1/2. So we could not find an explanation in the literature, although there are explanations. For instance, the same plot shows here that if we account for the kinetic modeling, then we cut the apex. I don't agree that the slope is the same. And then even if we take more effects into account, for example, the pH effect, it also cuts the apex, but that one is again horizontal. So the slope is not 1/2 as we can see in experiments. So we gathered more data. These data points are coming from experiment, and they mainly contain platinum and palladium. And we see the same slope with much more data. So should we continue trying to upgrade our computational workflow, not just at calculating absorption energy, not just taking scaling relations and plotting free energy diagrams, but also accounting for free energy barriers and coverages and pH effects and maybe ion effects, and then taking into account the whole electrical double layer. So basically running a molecular dynamic simulations of each reaction step, like shown here. Well, I hope that there is a simple explanation in terms of scaling relations that is actually a valid thinking approach, and it is called essentialism. And I believe that explanation may come from the scaling relations between some overlooked intermediate states. And thus, I propose that we might find an explanation by thoroughly applying specific effects. So in doing that, this map will be quite useful. It was proposed by Voivodich and Norskov, and it classifies different specific effects on a scale from electronic effect to the structural effect, which is basically what we call the geometric effect, and then distinguishing between extrinsic and intrinsic effects. And here you should basically find the cocktail, the strain and ligand effects, and many, many more. Just remember that each of them can have negative and positive impact on the activity, and the outcome of each effect can be rationalized in terms of the scaling relations. Let us turn back to the most general and conceptual level. There are 5 strategies for manipulating the scaling relations: tuning, breaking, switching, pushing, and bypassing. Other terms commonly used in the literature are overcoming and circumventing, and they perfectly fit here because overcoming is turning from tuning to breaking, whether circumventing is going beyond tuning using any other strategy. And we propose this term manipulating because it includes tuning as well. And the truth is that all the strategies are quite fruitful if we know how to apply them. So manipulating the scaling relations in general can signify improvement over what we have at the state of the art. And that is the main picture I would like you to remember after that presentation. Now I would like to remind that the paper is at Kermkive, openly available for everyone. And moreover, all figures you can find at GitLab, including the scripts, how we produce them, and vector graphics. There are also some cool notebooks at my GitLab where we have the animations you have seen in this presentation. And we played with AI a bit. So we created some podcasts, and that is about 1 hour long, but it was really fun to listen. There are almost no factual mistakes. This view on the scaling relation is a result of many joyful conversations between Jan, Ritums, Nadezhda, and myself. At the moment, we are scattered all over Europe. We work in different groups in Denmark, Estonia, Latvia, and Spain. But you know what? We established relations that keep us united across space. And I tend to think that in the same way, although there are many groups of catalysts in the vast chemical space, the scaling relations is the one concept that unites them all. So here's my last message for this talk. Think strategically about manipulating the scaling relations in your current and future research.